Welcome back friends, I am Rajdeep Acharya back again with another new lecture, and in this lecture we will be talking about thermodynamics first law, thermodynamics second law, enthalpy, entropy and Gibbs free energy. And this lecture is going to be very important for CSIR and it also. So let's start guys. Suppose guys it is a system. Suppose guys this is a system or this is actually a universe. System. So according to the first law of thermodynamics, energy, the total amount of energy, the total amount of energy in a system or in a universe is actually constant. So, according to the first law of thermodynamics, in a given system or in a universe, the total amount of energy is actually constant. The total amount of energy is actually constant, guys. And now we will be talking about the mathematical equation of first law. So basically, the mathematical equation is del E, which is actually the internal energy, equals to E B minus E A equals to Q minus W. So this is actually the mathematical equation of first law, guys. This is actually the mathematical equation of first law. And now we'll be talking about each of the parameters that we have been taken. So this is actually the del E. So del E is actually the internal energy. So del E is actually the internal energy. The EB is actually the amount of energy which is actually present, the amount of energy present at the end of a process. And EB is actually EA is actually the amount of energy present at the beginning of a process. So EA is actually the opposite of EB. That means the energy which is present at the start of this process, and EB actually stands for the amount of energy which is present at the end of a process. And now guys, we will be talking about the Q. Q is actually the amount of heat absorbed by system. And now guys, we'll be talking about W. W is actually work done by system. So W is actually the work done by system. So these are actually the parameters in this formula, guys. So these are actually the parameters of this mathematical equation, guys. So according to the first law of thermodynamics, energy of a system or if in a universe is actually constant. That means we can neither create energy, we can never destroy energy, and this is actually the mathematical equation, that is actually the del E, which is actually the internal energy, and it's actually the EB, which is actually the amount of energy which is present at the end of the process. EA is actually the amount of energy which is present at the beginning of a process. Q is actually the total Q is actually the amount of heat which is actually absorbed by a system, and W is actually work done by system. Internal energy is actually the change in energy. So I hope you guys have learned the first law of thermodynamics, and now guys we will be talking about the enthalpy before going to the second law, because at first we have to know enthalpy. So at first I have to remove this. So I am removing this. So what is actually enthalpy? This is the important question. What is actually enthalpy? So enthalpy, what is actually enthalpy? This is the question. So enthalpy is actually which is actually denotes by del H. Enthalpy is actually denotes by del H, and del H is actually summation of del E plus P del V. So here you guys can see that del H is actually the heat content, and del E is actually the free energy or free energy, and P del V, and P del V is actually the partial volume. So from this equation we can say that enthalpy is actually the heat content, which is actually the summation of free energy and partial volume. So basically it is actually the summation of free energy and partial volume, that is actually the enthalpy, which is actually denotes by H, which is actually the heat content. And sometime enthalpy is negative, sometime enthalpy is positive. It depends on the conditions. Okay guys, now guys we'll move to the second law of thermodynamics. Now guys we'll move to the second law of thermodynamics. So in the first law we have been talking about that energy neither be created, we cannot create energy, and we can never destroy energy. That means the total amount of energy is actually constant. But it is actually unknown to us that in a system a process is going on in a system, and whether this process is actually spontaneous or it is not spontaneous, I mean non-spontaneous. So to determine that a process in a system, whether a process that is going on in a system, whether it is actually spontaneous or non-spontaneous, a new concept comes. And this concept is actually entropy, which is actually the disorder of system. That is actually the entropy, which is actually the disorder of system. So entropy is actually the disorder of a system. It is actually the disorder of a system, guys. So suppose, guys, it is actually a system, or it is actually a universe. Suppose it is a system, and in this system a process is going on, and we know that energy is actually constant, and we can never create energy, we can never destroy energy. But a process is going on in a system, and in this case, if del S, which is actually denotes, entropy is actually denotes by del S. So del S is actually the entropy. So if in this case a process is going on in a system, and if del S, the entropy increase, that means this process will be spontaneous. And if, guys, the del S decrease, the entropy decrease, then this process will be non-spontaneous. That means in a system or in a universe, a process is going on, and this process will be spontaneous if the entropy increase, and if the entropy decrease, that means this process of this system will be non-spontaneous, guys. And now we will be talking about the mathematical equation of second law. Suppose, so it is actually S U double R O U N D I N G, surrounding, plus S system. That means S is actually the entropy denotes by S. So basically S means entropy of surrounding and entropy of system greater than 0. So this is actually the mathematical formula of second law of thermodynamics. And suppose, guys, we elaborate entropy again with an example. Suppose, guys, it is a jar, and it is also a jar. Okay, guys, it is jar number 1, it is jar number 2, and in this both jar there are some balls. It is one ball is second, is third, fourth, sixth, fourth, fifth, sixth. So there are 6 balls, and here also some balls. So if you look, guys, at this both jar, and if you notify these balls, you guys can see that in this ball, in this jar, the balls are actually in an order. That means they are not moving from one place to another place. But in this case, the balls are actually not in an order. That means they are actually moving from one place to another place. And if they are moving from one place to another place, and they are not in an order, that means there are actually disorder present, guys. That means the entropy is actually increasing in this case, as there are disorder present, and in this case the balls are actually in a order, that means there is no disorder, and we can see that there is no disorder, that means the disorder have decreased, so there is no entropy. So basically it is actually non-spontaneous and it is actually spontaneous, guys. So now we will move to the Gibbs free energy. Now guys, we will move to the Gibbs free energy. I hope you guys have learned what I am actually teaching you guys. So Gibbs free energy, Gibbs free energy. So the mathematical equation of Gibbs free energy is actually G del G equals to del H plus T del S. It is actually the mathematical equation. It is actually the mathematical equation of Gibbs free energy. And in this case, we can see that Gibbs free energy is actually the energy, I mean the amount of energy. G is actually the amount of energy. H is actually the heat content, I mean the enthalpy, and S is actually the entropy, and T is actually the temperature. So basically, if you guys look at this equation, you guys can see that this H came from enthalpy. S came from entropy, and enthalpy came from the first law, entropy came from the second law, and this entropy and enthalpy in this Gibbs free energy, it is actually a qualitative relationship. It is actually a qualitative relationship. So we can say that Gibbs free energy is actually the combination of first law and second law, and it is actually qualitative relationship between enthalpy and entropy. Sometimes enthalpy is positive and entropy is negative. Sometimes entropy positive, enthalpy negative, and on their positive negativity, the exergonic and endergonic will be determined by the G. So basically G is actually the free energy, and so we will be talking about the exergonic and endergonic processes. So suppose guys it is positive and it is negative, it will be negative. Suppose guys it is negative, it is positive, it will be positive. And suppose guys it is minus, it is minus, it will be minus, plus. If guys it is plus and it is plus, then it will be plus minus. And now guys we will be talking about those processes. So suppose guys this is positive, this is negative, that means enthalpy positive, entropy negative, and the Gibbs free energy become negative, that means it is actually exergonic or spontaneous. Suppose guys it is negative, it is positive, it will be positive, that means it is actually endergonic, that means it is actually non-spontaneous. NeOUS. Suppose guys both are actually negative, it will be actually positive slash negative. That means it will be on the spontaneous at low temperature. And if both are positive, then it will be positive slash negative, but in this time spontaneous at high temperature. So this is actually Gibbs free energy. So I hope you guys have learned something from this tutorial, and I hope this video will help you if you are in it also. And thank you so much for watching this video, and also share this video among your friends who are in need of this video, of this lecture. Thank you so much guys for watching this video. Also like and subscribe this channel. Thank you.